In this lecture, we'll learn how to handle exceptions in the RISC V processor. First, we'll look at some special registers in the RISC V processor that we have not studied yet. One of them is the cause register. The cause register is used to encode the reason for an exception or an interruption in the RISC V processor. It's called the uCause register. It has 32 bits, and the bit 31 is used to indicate whether what occurred was an exception, which is caused by the execution of an instruction in the program, such as a segmentation fault, an non-aligned address, or whether it's an interrupt, which is caused by an external event. And the bits 0 to 30, the remaining 31 bits, is reserved for the exception code, which will indicate the cause of that exception. Then we have two registers, the control and status registers in RISC V that we're going to pay special attention to. One of them is the status registers called the U status that will have this format. And the most important bit that we're going to worry about in this register is the bit 0. If the bit 0 of the status register is 0, the interrupts are disabled, and if that bit is 1, the interrupts are enabled. And then we have the interrupt enable register, or UIE, for user interrupt enable. And in that register, we're going to be especially interested in two bits, the bit 8 that enables external keyboard interrupts, and the bit 4 that enable external timer interrupts. The reason that we're going to be especially interested in these two registers is because we're going to be having a lab in 229, and in this lab we will be handling interrupts from the keyboard and interrupts from the timer. So we're going to have to make sure that those bits are 1 when we run our labs, so that those interrupts are enabled. There are several instructions that we can use to manipulate the value of the control status registers in RISC V. So remember that CSR stands for control and status registers. Here is a group of 5 control and status registers that we pay more attention to: the user level cause, the user level status, the user interrupt enable, the user exception program counter, and the UTVEC. RISC V actually defines 4,096 control and state registers, and each instruction that manipulates a control and state register has a 12 bits to specify which one of the 4,096 control and state registers that instruction should manipulate. There are several instructions that are atomic read, modify, write operations in with the control and status registers. A read, modify, write operation means that the processor will read a value, do a modification to the value, and write the value all in a single operation without any interruption from anything else. So the first instruction that we're going to take a look at is the atomic read-write control status register. This instruction is called CSR-RW, so control status registers read-write. It has the specification of 2 registers. In this case, we are using T0 and T1, and the number of a control status register. In this case, the control status register specified is the control status register 0. And what this instruction is going to do are 2 things that are going to happen at the same time atomically. The first thing is that the value in the control status register will be 0 extended to the size of T0. In some implementations of the RISC V architectures, those 2 registers will have the same size. In other implementations, they will not. So if they do not have the same size, the value that is in the control status register will be 0 extended before written into T0. And then simultaneously, at the same time, the value of T1 will be written in the control status registers. So that number in the instruction specify which is the register that I'm operating with. And in this case, the CSR0 is the U status register. So what this instruction is doing, let's suppose that this is the value in T0, this is the value in T1, and this is the value in the control status register 0. The instruction we're going to do at the same time move the value that was in the control status register to T0 and move the value that was in T1 to the control status register. Note that I could have specified T0 as the second register in this instruction. In this case, I will have a swap between T0 and the control status register 0. I just used a different register here, T1, to illustrate the more general form of the instruction. Most of the time when using this instruction, you're going to be using this instruction to swap the value that is in a register, in a RISC V regular register, with the value that is in the control and status register. Another instruction that's available to you to manipulate the control and status register is the atomic read-write control status register, just like before. But now, instead of specifying a second value, second register, what I specify is an immediate value. So now what will going to happen is that the 0 extended value of the control status register will be moving into T0, and the 0 extended immediate value will be moved in the control and status registers. So here's what happens. Let's say the T0 has the value 42, the control and status register has that value. What will going to happen is that at the same time, atomically, the value from the control status register will move to T0. The immediate value will be moving to the control and status registers and will be 0 extended to 32 bits. Another atomic read and write instruction is the atomic read and clear bits in the control and status registers. So in this case, I have again the specification of 2 registers. And what is going to happen is that again we're going to take the value of the control status register specified, in this case it's register 0, and I'm going to 0 extend that value and put it into T0. And then I'm going to take the value of the control, the value of T1, I will complement that, so I will flip all the bits in that value, and I'll do a logic AND operation with the control status register. The effect of that will be that any bit that is 1 in the T1 will be forced to be a 0 in the control status register. That's why this instruction is called the clear bits instruction. So for us to understand what's going on in the example, let's say again that those are the values in the T0 and control status register, and that's the value in T1. So let's first think about what should happen in this case. What should happen in this case is that any bit that is 1 in T1 has to become a 0 into the control and status register. So if I look at the control status register, I want to 0 the upper half of the control status register with this instruction. But I do that after making a copy of the original value of the control status register into T0. So here is what happened. Pay attention to what happened with not only the data movement, but with the change of the value into the control status registers. So the value of the CSR goes into T0, and then the value of CSR changes so that the upper half of that register is now all zeros. So whenever a bit is 1 in T1 here, that bit has to become a 0. The corresponding bit has to become a 0 in the control and status registers. I can also do an atomic read and clear bits in CSR where I do not use a second register to specify which bits are going to be clear. I use an immediate value. So again, that bar means negation. So I'm going to negate the value of the immediate value and then do an AND with CSR. In this case, what it means is that the bit 0 of CSR has to become 0 after I executed this operation. So this is for the case where I only want to flip a few bits, to clear a few bits. I may be able to do that with an immediate value instead of having to load the position of the bits that I want to clear into a register prior to the execution of the instruction. So what is going to happen here is similar to before. The value of CSR0 will move into T0, and the bit 0, if you compare these two values now, you're going to see that the bit 0 got flipped from a 1 to a 0 because my immediate had a 1 in the least significant bit. Next, I have an atomic read and set bits in CSR. So this is a very similar instruction with the clear bit, but now I specify which bits I want to set. Again, if I look at this example, what is going to happen now is that after, I'll make the copy of CSR0 into T0, and at the same time, I'm going to be setting the upper half of the word in CS0 to 1s, because now every bit in T1 that is 1, the corresponding bit in CSR0 has to become 1. So what happens is this, that value moves, and then the upper bits of the control and the stats register 0 become all 1. Next, I have an atomic read and set bits in CSR, but now I use an immediate value instead of using a register. So similar to before, but notice that now the lower significant bit of the register, I set in the bit 4 to 1. I have the number 4 in the lower bit. So what is going to happen is that I'm going to switch, this is an error in the animation. What has to happen here is that the number has to become a 4. No, it has to become a 5. I'm going to have to correct this animation in the actual slides. The correct thing here to do would be, let's look at this together. So this is the number 4. So this has the bits 1, 0, 0, 0. And this is was the number 1. So this would have the bits 0, 0, 0, 1. So 4 or 1 will become 5. And this bit should not change. I'll fix that in the slides after I finish the recording. So the organization of the RISC V coprocessors is such that I have the RISC V coprocessor has the CPU that we are very used to, X0 to X31 are the registers. I have the arithmetic unit. I have the memory. And now I have the control stats registers that are in this position, and I have something else. I have the floating point processor, which we're going to study after we study interruptions and exceptions.